Hi, welcome to part 2 of this series of videos about the best methods to acylate amines. This presentation is about the use of other, less reactive acylating reagents than acyl halides. The focus will be on electrophiles that can be isolated and stored, while those prepared just before or during the acylation reaction will be discussed in part 3 of this playlist. Many different electrophiles can be used to convert amines into amides, but only few of them can be isolated and offer a practical, convenient alternative to acyl chlorides. The most relevant acylating reagents are carboxylic anhydrides for acids of low molecular weight, various so-called active esters, imidazolides, thioesters, and for highly nucleophilic amines, even simple aryl or alkyl esters. Less reactive acylating agents offer a number of advantages if compared to acyl halides. Because of the lower reactivity, these reagents are often better suited for the selective acylation of multifunctional amines. The risk of hydrolysis or ester formation from alcohols is lower and no corrosive halide waste is generated. Enantiomerically pure acylating reagents with the center of asymmetry and hydrogen at the alpha position will be less CH acidic and more configurationally stable than the corresponding acyl chlorides. Ketenes will also be formed less readily than from acyl halides. The main disadvantages are their higher price and the occasional large amounts of waste. Then N-hydroxybenzotriazole is explosive, and the carbodiamides often used for the preparation of active esters are quite toxic and can cause allergies. One practical way to acetylate amines is to heat them with acetic anhydride. Because acetic acid is a weak acid only, no auxiliary base is usually required, in particular for amines of low basicity. In this example, ethanol was added to prevent esterification of the product, but the high yield obtained indicates that the amide was formed much faster than any ester. Also, anilines, even unreactive ones, can be easily acetylated with acetic anhydride without any auxiliary base. In this example, a rather unreactive 2-aminopyrimidine was acetylated by refluxing with an excess of acetic anhydride. Occasionally, though, an excess of acetic anhydride or long reaction times can cause the twofold acetylation of amines. I'll show you an example at the end of this video. Even sterically demanding anilines can react cleanly with acetic anhydride. Again, a high yield was attained and no additional base was required. This is a procedure for the twofold acylation of glutathione with butyric anhydride. The reaction was conducted in water in the presence of an excess of sodium bicarbonate, and acylation of the thiol group could not be prevented. With more powerful acylating reagents under anhydrous conditions, mixed anhydrides could have been formed with the unprotected carboxyl groups, what in turn could cause the formation of byproducts. With the Schotten-Baumann technique this did not occur, however, and a high yield of the desired peptide was obtained. Anhydrides do also react with aqueous ammonia, as in this example. Despite the moderate excess of ammonia only, a high yield of the expected amide was obtained. In the presence of enantiomerically pure nucleophilic or hydrogen-bonding catalysts, racemic amines can sometimes be acylated enantioselectively, as in this example. To suppress the uncatalyzed benzylation, the acylation was conducted at -78 degrees Celsius. The solid phase synthesis of peptides is conducted by acylating the resin-bound peptide amine with a carbamate-protected activated amino acid. This strategy has the advantage that activated carbamate-protected amino acids do not racemize by oxazolone formation as readily as acylated amino acids. In this example, however, such an activated peptide acid was used as electrophile, namely a hydroxysuccinimidyl ester. The acylation was conducted in aqueous THF with bicarbonate as auxiliary base. Fortunately, no extensive racemization of the phenylalanine residue occurred. This here is an example of the acylation of a racemic morpholine with an enantiomerically pure active ester, the chirality residing, however, in the leaving group. The acylation proceeded with moderate enantioselectivity. In this example, the difficulty was again to prevent the formation of an ester. This was accomplished by using a thioester as electrophile in ethanol as solvent and with the weak auxiliary base N-methylmorpholine. Simple alkyl esters are much less reactive than the electrophiles presented up to now. Even among esters there can be large differences depending on the acidity and steric bulk of the alcohol. As shown here, carbohydrate or glycol-derived esters react, for instance, about 10 times more quickly with liquid ammonia than ethyl esters. Still more electrophilic are aryl esters and vinyl esters. Ethyl and methyl esters are usually too unreactive and require some catalysts to react with amines quantitatively in a reasonable amount of time. Ammonia is particularly unreactive, and even in concentrated aqueous solutions, water can sometimes compete with ammonia for the electrophile. In the example on this slide, acetylation of aqueous ammonia with butyl and methyl acetate took 100 hours and 20 hours respectively, but about 10% of the esters were hydrolyzed, despite the large excess of ammonia. Anilines are still less nucleophilic than ammonia, but the reactivity can be enhanced by deprotonation. Interestingly, despite the strongly basic reaction conditions in this example, no acrylate was formed by elimination. Much more nucleophilic than ammonia are alkyl amines, and a high concentration of these do sometimes react cleanly with a simple methyl or ethyl esters. In this example, an excess of methylamine in ethanol was used to convert alanine methyl ester hydrochloride into the corresponding methyl amide. No significant amounts of dipeptide were formed because amino acid esters are much less nucleophilic than alkyl amines. The electron withdrawing effect through sigma bonds of the alkoxycarbonyl group lowers the pKa and the nucleophilicity of such amino groups significantly. Despite the high nucleophilicity of pyrrolidine, almost no reaction occurred if a slight excess of pyrrolidine was heated with ethyl phenyl acetate to 50 degrees Celsius for 24 hours. The Lewis acid lanthanum triflate did, however, catalyze this reaction effectively, as shown here. Even Brønsted acids can catalyze this reaction, and mixtures of an alkyl amine with less than one equivalent of acetic acid can sometimes cleave simple alkyl esters, as in this example. Similarly electrophilic as aryl esters are vinyl or isopropanil esters. Here, the methyl ester of phenylalanine was acetylated in high yield by treatment with isopropanil acetate and catalytic amounts of 1,2,4-triazole and DBU. One alternative to liquid ammonia or concentrated solutions of ammonia is formamide in combination with an alkoxide. Here, formamide and sodium methoxide were used to convert a sterically crowded, unreactive diethylmalonate into the amide. The authors proposed that the reaction proceeded by intermediate formation of an imide. Despite the higher selectivity, also the less reactive acylating reagents can bring about unexpected side reactions. One of them is the formation of imides if an excess of acylating reagent is used and the reaction is allowed to proceed for too long. In the example shown here, despite the absence of auxiliary bases or catalysts, a large amount of imide was formed as byproduct during an acetylation with acetic anhydride. Similarly, an excess of acylating reagent enforcing reaction conditions can cause the dehydration of amides to nitriles. Sterically crowded, unreactive methyl esters can sometimes act as methylating reagents instead of acylating reagents. This happened in the example shown here, where only 29% of the expected amide was obtained, along with a large amount of the carboxylic acid and the methylated amine. The trichloromethyl group is a good leaving group, and trichloromethyl ketones are powerful acylating reagents. Similarly, esters of trichloroacetic acid do not exclusively yield amides upon reaction with amines, but can also yield carbamates, as shown here. The released chloroform can undergo alpha elimination and give dichlorocarbene and numerous unwanted byproducts, such as for instance formamides. Trifluoroacetic acid esters do not react in this way and are useful reagents for the conversion of amines into trifluoroacetamides. When acylating alpha amino acids, one additional potential side reaction is the formation of acylated aminoketones, the so-called Dakin-West reaction. This is an acylation at carbon of an intermediate oxides alone and usually requires some auxiliary base and a high reaction temperature. Even some activated carboxylic acids with a high tendency to enolyze, such as acyl chlorides or aryl acetic acids, can be converted into ketones by heating in the presence of pyridine. On this and the next two slides you can find a short selection of some further examples, which is also in the description of this video. Many examples of the use of alkyl esters as acylating reagents for amines have been reported. Most require some catalyst, for instance strong bases, organoaluminum reagents or enzymes. Here are some further examples of the use of thioesters, imidazolides, imides or other amides as acylating reagents. As mentioned earlier, most amides are unreactive, but in the presence of catalysts or upon strong heating, even amides can act as acylating reagents. The next presentation of this playlist is about the in situ activation of carboxylic acids. This is a common strategy for the preparation of amides, in particular peptides and other structurally complex amides. So don't miss it.